Welcome back, students. So, today we will be continuing the NMR spectroscopy. We will be having lecture 7, which is the chemical shifts in NMR. So, in the last lecture we have seen the introduction to NMR, its fundamental and its concepts. Here we will see what is the chemical shift, and also we will learn something about the nuclear magnetic resonance spectrophotometer. So, going ahead. So, what are we going to learn in this particular lecture? We will see what are the definition of chemical shift. Then we will see what do you mean by shielding and deshielding of protons. This is very important concepts, because the shielding and deshielding concepts, if you know, if you understand correctly, then you will be able to solve many of the NMR spectra for unknown molecules. Then the NMR spectrophotometer, we will see the two modes, the continuous mode, continuous wave, and then we will see the pulse mode, both continuous wave and the pulse mode. Then we will see some quantification, how you can quantify the amount of the particular components in a mixture. And finally, some examples. These examples will be varied examples, we will see for different molecules, aromatic, straight chain, branched. Okay. So, let us go ahead. So, what we saw is that we have a nucleus here, and if you apply a magnetic field, because we are applying magnetic field in an NMR spectrophotometer, if you are applying magnetic field, now how this magnetic field is going to interact with the nucleus? There are two ways of using it or understanding this concept of chemical shift. That is, for example, you assume two cases, one where the nucleus is surrounding by electrons which are of low electron density. So, these electrons, when I talk, it relates to the valence electrons. Okay. The valence electrons are circulating around the nucleus. So, if these are circulating around the nucleus, so it means they will be having certain, because it is moving across. So, if it is moving in this manner, okay, all the nucleus is moving, suppose in this manner, not nucleus, the electrons, if they are moving in this manner. So, this if we are moving, so it means with the moving electrons, electric field is generated, and with the electric field, your magnetic field is also generated because of the continuation rotation of these electrons, and this electric field has then causing a magnetic field which is actually opposing the applied magnetic field. Okay. So, this is this direction. So, you apply one magnetic field from outside and you have electrons circulating around the nucleus, you have an electric field, and because of the electric field you have a magnetic field which is opposing the nuclear field which is applied. So, now in both the condition you have low electric density and high electric density. When you have a high electron density, in this case let us say it is a proton molecule. So, if it is a high electron density, it means what? So, you have a higher and higher current here, okay. Here also higher electronic currents, these are higher. So, if higher electric field means higher magnetic field. So, you will have more and more opposition to this electric field, okay. So, if it is having a magnetic field, so opposing, so it means the nucleus will experience a weaker magnetic field. So, the electrons are more here. So, high electron density will have more electron shielding. So, it will not allow the external magnetic field to interact in the higher manner as compared to a low electron density. So, now the question comes, this low electron density when do you observe, and the high electron density when do you observe? See, the low electron density you will only observe in the case where you will know the particular nuclei, in this case it is hydrogen nuclei, is attached, let us say to some atom, let us say oxygen atom. Now, oxygen is electronegative, fine, for example. So, what it will do? It will try to attach, or it will try to take up all the electronic cloud from the hydrogen towards itself, okay. So, if the electron cloud is shifted from the hydrogen to the oxygen, so what will happen is you will have lower electron cloud onto the nucleus. While in this case, for example, we thought this is something like oxygen and hydrogen, here carbon and hydrogen. So, as you know, carbon is quite less electronegative than oxygen. So, it will attract less electrons towards its side. So, it means the electron density remains higher in the neighborhood of hydrogen. So, that is why both these two different environments will behave differently with respect to the incoming magnetic field. This is exactly what is called as chemical shift. So, here you have a higher electronic field, so we call higher magnetic field experiencing, or maybe we can write in other manner, instead of higher we can say higher opposition, or we can say less electron shielding, because of less electric field. Okay. So, this particular term is called as downfield, and the other contrary term is called upfield. Okay. So, if you know this electron cloud, so then you will be easy to understand the subsequent slides. So, it means that if it is a less electron shielding and less electric field, so this will absorb more energy. This will absorb more energy as compared to the high electron density. It will absorb less energy. Why? Because the magnetic field is not able to penetrate through the electron cloud, while it is easily able to penetrate to the electron cloud. So, this will be higher electron density will absorbing less energy. So, moving ahead. So, to summarize what we saw, protons have a range of resonance frequencies depending on the intensity of the applied field. Okay. Different protons at different parts of the molecule will absorb in different manner. This is obviously, but this will be perplexing for scientists, because suppose if I use a magnetic field, let us say 60 megahertz, then okay, another particular scientist or another lab uses 100 megahertz, another one uses 200. So, they will all show up at different energy. So, some may absorb at 60 megahertz, another one absorbing 100 megahertz. So, can we unify this particular magnetic field in some manner? Let us see. To prevent this ambiguity, this is why a new chemical, this parameter is created. This is called chemical shift, which I just now called. So, instead of telling okay, at this particular frequency you have this much of absorption, and this particular field, when I talk of field, it means frequency, you have this amount of absorption. Can we use a component which, let us say it is a reference compound which is 0. So, we use that compound which is called tetramethylsilane. Okay. It is methyl group all attached to 4 methyl group attached to silane. Now, the question is why is this? Because it is said that this compound totally shields the nucleus. So, if it totally shields the nucleus, it means the total energy it is absorbing is absolutely 0. So, it is not absorbing any energy. So, that is why we can assign 0 value for this particular compound, that is trimethylsilane. So, now it is fine, the scientists have now agreed the unifying factor may be tetramethylsilane, fine. Now, then still do we have enough information? Because these shifts will also depend upon what is the magnetic field being applied. So, for 60 megahertz the shift may be different, 100 megahertz it may be different, likewise. So, still we are not up to, and we have not got through the solution. Let us see how we solve this. So, again just summarizing the shielding part, each proton is having a slightly chemically different environment. All protons will not resonate at the same frequency. As I told you, different protons at different areas will resonate in a different manner. Protons are either shielded from the magnetic field by the electrons surrounding them. A current is formed when electrons circulate. This current produces a secondary magnetic field, as I told you. So, you know, this is the nucleus, and if you have this types of electrons, it will produce a secondary magnetic field. So, these are moving like this. Applied field is B, it will try to oppose this field. This is called the secondary magnetic field, and this entire term is called as diamagnetic shielding. Okay. So, you should keep in mind these terms. So, more electrons surrounding the proton, the stronger is the counter field, as I told you. Because the proton is exposed to a less magnetic field, its frequency will drop. So, precessional frequency means, as I told you, if this, just again recollect the last lecture, and if I draw like this, so this is what it is, and if I draw like this, so this is the precessional frequency. So, this precessional frequency will drop if the entire nucleus is shielded, that is what it says. As a result, the proton absorbs at a lower frequency, okay, this is a lower frequency. This is the fact because of each proton based on the unique environment has a unique frequency, because due to this fact each of the frequency will have different frequency. For example, let us see a molecule called aldehyde, okay. So, this is a spectra which I will explain in detail, but let me tell you. So, if 0 means this is the position which is trimethylsilane exists. Now, what is the shift? For example, I apply a magnetic field of let us say 60 megahertz. So, if it is 60 megahertz, what is the shift? How much it is deshielded with respect to trimethylsilane, that is given here. So, this is heavily shielded. So, more the peak is shifted to the left hand side, lesser will be the shielding, okay. A more close it is to 0, heavily it is shielded. Now, see these two different attachment. You have the methyl group and you have the CH group, okay. So, this is a hydrogen here, okay. So, this hydrogen, because of the electronegative atom oxygen, the hydrogen's electrons are attracted more so to the oxygen atom. Because of this, electron cloud is less on this particular atom. Because of that, it is absorbing higher frequency or higher energy and it is showing up here. So, this CHO, this entire attachment. So, if this type of frequency is present, it will show up at 9.72. So, this 9.72, it is obviously also depend upon the frequency applied. Still we are not there, we are not having an answer. So, if I change it to 200 megahertz, my question is, will my values change 9.72? So, that is our question which we have to answer in the subsequent class. Now, C for methyl group, this C is connected to 3 hydrogen atom and this carbon, it is shielding. So, it means it is not taking away much electron cloud from the, or it is not distorting the electron cloud from the hydrogen atom. So, we say it is heavily shielded. So, this is what you see a different atoms lying in different chemical environment. So, proton in the same chemical environment will obviously have same chemical shift. So, if this is a aldehyde group, for example, it will show more or less near about 9.72, something like that, okay. That is what it implies. So, for a particular proton, the shift from the TMS is dependent on the intensity of the applied magnetic field. A proton's resonance frequency is about 60 megahertz in an applied field of 1.41 Tesla. We saw this earlier. Sorry, this will not be 23,400, it will be 14,100. Okay. While it is roughly 100 megahertz when the field is 2.35 Tesla. So, you see there are difference in frequency which is absorbed. Now, can we take a ratio? The ratio of the resonance frequency to the true field obviously will be the same. So, it means the shift in hertz from TMS is, we can say, 5/3 greater for a given proton in the 100 megahertz range when compared to 60 megahertz range. So, if I divide the magnetic field 100 by 60, this is proportional to the values in Tesla 2.35 to 1.45, which is equal to 23,500 and 14,100 Gauss, and these will be related to 5:3. So, the shift from TMS is 5/3 greater. So, if you have a 100 megahertz field, the particular shift will be 5/3 times greater than that observed in 60 megahertz. Hope you understand. So, we will see more example, then it will be much more clear. So, now the problem is still we are away. So, what we do is readily we dissolve, this is resolved by defining a new parameter which is independent of field strength. We do not want to bring the field here. So, what we do is we divide the shift of a particular proton by the frequency of megahertz of the spectrophotometer. Now, the frequency in megahertz of the spectrophotometer, it is supplied by the instrument, okay, and the chemical shift you get is again due to that particular magnetic field. So, can we divide those two? So, if the shift, let us say from 0 to this part 1, 2, 3. So, this shift, suppose this is a shift, it is in hertz. For example, can we convert it into hertz, and the frequency is what you are applying through the instrument. So, if you divide them, this will becomes the shift which is somehow related to this distance. So, the shift in hertz is nothing related, but it is related to the chemical shift, that is delta. The chemical shift here indicates the degree by which the proton resonance is moved away from TMS. This will always be expressed in parts per million, because it is hertz here, it is megahertz here. So, megahertz means 10 to the power of 6. So, you have parts per million, okay, ppm. So, it will be ppm of the spectrophotometer fundamental frequency. Even if the test is performed at 60 megahertz or 100 megahertz, the value of this chemical shift is always the same, because now you are taking ratios, ratio in hertz to the frequency in megahertz. So, if you see at 60 megahertz, you are getting a shift of 162 hertz, and at 100 megahertz you are getting a shift of 270. So, divide them, you will get a uniform answer, that is 2.70 ppm. Okay. This you should clearly observe and see what we mean by chemical shifts, parts per million. So, it has been approved that to record chemical changes in these units or parts per million, we use the primary spectrometer frequency. So, for TMS it is 0.00 ppm. So, it means TMS is here 0, 2, 4, 6, 8, 10 and likewise. So, more you go to this direction, higher you go to the left hand side, more will be the deshielding. More you go to the right hand side, more will be the shielding. So, electron cloud is dense here, electron cloud is very less here. So, now let us see how actually the NMR spectrophotometer measures this. So, we have two instruments, the continuous wave instrument and the pulsed Fourier transform instrument. The continuous wave NMR spectrometer operates by modulating the magnetic field intensity using a constant frequency radio frequency signal. So, you send a constant frequency signal to the particular sample, and the precessional frequency will obviously rise when the magnetic field intensity is raised. So, as the precessional frequency exceeds 60 megahertz, it will exhibit resonance. So, what you have is you have a frequency which is sent to 60 megahertz. Now, if it is exceeding 60 megahertz, the magnets where you use to generate the magnetic field in such a manner that it can generate 60 megahertz plus or minus 10 ppm of chemical shift. So, if it exceeds 60 megahertz, then it will show a chemical shift. The shielded protons appear to the right of the chart, while unshielded protons appear to the left. Just now I have just now explained this. By changing the magnetic field, the area to the left of the chart is often referred to as downfield. The region to this is called as, to the right is called as upfield. Okay. Continuous wave devices constantly alter the magnetic field, scanning the spectrum from downfield to upfield. Now, all the frequencies may not be same. What you do is you try to change the frequencies. So, it means if you have this something like this 60 megahertz, it starts, you go to this direction, let us suppose there is a chemical shift. So, it means what, you send one frequency at 60 megahertz, then 60 plus corresponding whatever the magnetic field you add up in hertz to 60, then 60 plus something which you add up to 2, like that you keep on changing the frequencies from downfield to upfield. Downfield is and upfield is one where the electron density is very less. For example, if this concept you have the spectra of phenylacetone, okay. The phenylacetone is you have a ketone group here. So, the blue ones are the locations, okay, of the particular spectra. See, so it means that this proton at the aromatic ring are all equivalent. So, there are 5 protons 1, 2, 3, 4, 5, all these 5 are clubbed here. I will tell you later in the next lecture how does this splitting of this particular peaks takes place. That is a different concept together, we will see up, we will discuss this later. Then you have one which is not there. So, because of the resonance you have again diamagnetic current. What it does is the electrons gets rotated around the aromatic ring. So, the electrons is actually shared. Because of this sharing it is deshielded, and because deshielded you have at a higher field. So, it will absorb at a higher frequency. Like that the 2 protons are the one which are at here 3.45, these 2 protons, and you have 3 protons which is the more shielded, highly shielded, which is appearing here. So, if you see, more or less you will come to know that the results are due to 3 protons, 2 protons, 5 protons. So, they are behaving equivalently. Now, if you have a sample like this and you pass a wave, and if you pass a particular radio frequency, it will and then sweep, then you will have something like this. You will have a wave which is going in this manner, it will decay with time. What does this mean? Ringing. Ringing means if you pass energy to this sample, the nuclei will vibrate, it will get a transition from the spin state plus half to minus half. But then if you remove the magnetic field, it has to come back to its original position. So, it has to relax. This relaxing is a very slow process. So, if the sweeping direction is faster than the ringing direction or the ringing phenomena, so you will have a ringing type of behavior appearing where the waves decay slowly with time. So, that is what I have written here, that ringing will happen when the simulated nuclei does not have enough time to return to their equilibrium condition. So, relaxation rate of the stimulated nuclei is lower than the scan rate. As a consequence, they continue to produce an oscillating and quickly fading signal called as ringing. Okay. Now, issue is in the continuous wave, we are simulating a nuclei of one kind of isotope at a time. So, let us say we first put up a frequency, then we see whether there is some resonance and we record that. Then increase the frequency, again see whether is there a resonance of other thing, other nuclei, again we record it. Like that we keep on increasing the frequency and we obtain those nuclei which is having resonance. So, but the issue is there are so many different types of proton, phenylic, proton, vinyl, methyl and so on. So, and they all excited independently of the others, because they are all excited at different frequencies or different absorption. So, now can we reduce this time? Can we not send one by one? It is similar to like what we discussed in infrared spectroscopy. You recollect, we have the dispersive and the Fourier transform. Same way we have continuous wave and the pulse wave. So, in this continuous wave you are sending one by one, similar to dispersive. So, can we do it at one go? So, yes, we can do it. What we do? We use a pulse signal. The pulse signals means you send a brief burst of energy which is called a pulse, which will simultaneously excite all the magnetic field in the molecule. Now, it is something like that, if you send a pulse signal, it means that pulse signal will be not a solid fundamental frequency, because you are not giving entire time, you are not giving sufficient time so that the wave goes and reaches a solid vibrational frequency. So, it will have several frequencies encoded within that pulse. So, this is the advantage of it, since you are sending all the frequencies at a time, it has to be brief. So, it is between 1 to 10 millisecond because of the Heisenberg uncertainty principle. Okay. So, you send a 90 megahertz for example, in this case for a 2.1 Tesla magnetic field for this much time period. So, now what you do is the source is rapidly switched on and off, producing a pulse. put it on, put it off, like that you send a pulse of energy through the sample. So, as a result, the pulse includes the spectrum of all the frequencies encoded in the center. So, I will show a figure below, next figure, where I will discuss the spectrum of frequencies. The range of these frequencies is sufficient to activate all the molecules different hydrogen types simultaneously. Earlier it was one by one, serially it was happening, now it is simultaneously. When the pulse is interrupted, the excited state will obviously lose their excitation energy and it return to its natural spin state. When I talk of natural spin state, it means I am talking about the regenerative pair. So, each excited nucleus will produce a electromagnetic radiation as it relaxes. So, this is what. So, if you send a pulse on short time period in milliseconds, stop, you are stop, there is a pulse. So, it means that if that pulse is there, some frequency will be developing as shown here. This is the frequency. This frequency will be encoded with lot of frequencies together. Because of this encoding of frequencies together, it will be able to excite all the nuclei simultaneously. As the fact that it includes many nuclei, so you use multiple frequencies. This is actually resulting in what we called as free induction decay signal, FID. The strength of this FID decay, because all the frequencies will ultimately have to decay because you are releasing the energy after a burst. So, it will lose their excitement. The FID is a superimposed mixture of all the emitted frequency and may be very complicated. So, like Fourier transform IR, FTIR, here also same thing, you will have a signal which will having emitted frequency of different waves. So, now if we want to extract the frequencies, you again apply through a computer, and this technique is called Fourier transform analysis. So, this is actually what in our IIT Guwahati, the central instrumentation facility, the spectrophotometer looks like. So, this is of 600 megahertz, and this is actually you have in this particular shell, this shell you have the sample which is inserted here. This is a sample, these are different tubes which are inserted here, and in this you have the magnetic, a strong magnet connected, and the radio frequency which is detecting the frequency of the absorbed waves likewise. And you also need a coolant, this coolant are somewhere here. So, why you require a coolant? So, the coolant is required to, because you are sending magnetic field of 600 megahertz, the magnet gets heated up. So, to cool that you need a coolant, it is usually of helium. So, this is what the diagram looks like, the flow diagram. So, this is the sample tube, you have a sample tube inserted inside a magnet, this is the magnet. So, what we do is you control the magnetic field using the magnetic controller. Okay. If I send a electric current through a magnet, it will produce a magnetic field, that is why it is coupled to the magnet. So, as you send the different electric field, magnetic field will change. If the magnetic field changes, it will also show up in this particular sample, it will interact with the sample own inherent magnetic field, whether it is shielding or deshielding, and this will be detected in a detector how much it is absorbed, and you have a radio frequency transmitter to show that how much of it waves is generated, what is the frequency of the wave which is generated through this magnetic controller. So, one end you have a transmitter and one end is a detector. One it detects the particular waves which are absorbed, it is absorbed, then you go in a printer. I mean, here you have all the Fourier transform being applied to those waves, and you get this spectra, which is the intensity versus the magnetic field. So, as I told you, there are 4 parts: the magnet, which has a controller to produce a specific magnetic field, a radio frequency source, a detector to detect the output signal, to record the output and plot it against the magnetic field, which is the recorder. Okay. Some other details is a sample is taken in a glass tube. So, obviously, if you see, it is placed between the 2 poles of a magnet. The sample is then exposed to radio waves, frequency kept constant. So, as I told you, you actually alter the magnetic field, you generate radio frequency, and this radio frequency is kept constant. Then the tube is spun around at a steady state. You saw that tube, it is spun in a steady state such that all parts of the sample get equal exposure. So, the sample should get equal exposure to the radiation and the magnetic field. Using this electromagnetics, the magnetic field strength is varied. Okay. So, all this is done in a, let us say, within a time period of seconds. So, now do we take the sample directly? No, we cannot take the sample directly, because the issue is the precessional frequency of the proton. Here we know it is matches with the frequency of the incident solvent, but you need to dissolve in a particular solvent of 0.5 to 1 ml of solvent. Why? Because such solvent is required, like in KBr, potassium bromide we saw infrared spectroscopy, it should not absorb the infrared. Same way, we need to choose a solvent in such a manner it does not have any nuclei. You want to dissolve something, you do not do it directly, because otherwise the peaks will be not be comparable. So, we do that, we use a deuterated form of solvent. For example, some are heavy water, D2O, deuterated chloroform, or dimethyl sulfoxide deuterated form. So, these samples do not contain protons. So, deuterium being NMR active does not resonate along with a proton. Okay. Now, if you see, for example, for acetone, if you apply the radio signal, the acetone here contains just one kind of hydrogen. All 6 hydrogens are equivalent. Okay, acetone. Okay, the acetone, all the hydrogen are equivalent. So, it means that as the nuclei relax, the signal decreases, the signal decays exponentially with time. So, this is decaying exponentially with time. If it does not decay, it will look something like this, it will look like a cosine wave. Due to the fact that the horizontal axis involves time, because you know the decay is with respect to time. So, we are getting something in time series. So, this has to be converted to frequency series. So, that is why we use this Fourier transform. So, that is what we are just now discussed. So, we get the signal from the instrument as a time domain signal. So, the frequency of this wave may be calculated from its observed wavelength. The frequency obtained is not identical to the frequency emitted by the methyl hydrogens. Okay. Now, please understand, we are sending a pulse of this frequency. So, that pulse frequency is not a solid frequency, solid fundamental frequency. So, the frequency you obtained from this particular sample is not identical. The fundamental frequency of the pulse is not same as acetone fundamental frequency, because this decay is an interference signal between the radio frequency source, which is 300 megahertz, and the frequency produced by the excited nucleus with a wavelength equal to this. So, I can write this expression, the wavelength of the particular frequency which is coming out is nothing but the reciprocal of the difference in frequencies of the fundamental of the frequency which is coming from acetone minus the frequency of the pulse. But how do we get the actual frequency of acetone? So, we get the signal which is actually reflecting the frequency difference between the two. Because of the pulse frequency is known, because we know what is the pulse frequency, because this is what we apply to the sample. So, we can easily calculate the precise frequency. So, we did not need to know this information, since we are only concerned with the chemical shift of the protons. So, what we do is that we know the wavelength which is coming out from the spectrophotometer, and we know the particular frequency or the wavelength of what is input. So, can we divide them? If we divide them, because it will be having some units based on hertz with respect to megahertz. This is very similar, analogically similar to the one we just now described, but still this chemical shift is not the actual chemical shift, because this actual chemical shift is not the fundamental frequency. Fine. So, what I did is just took the difference and the input. Likewise, what I said, it was the magnetic field in hertz by the initial magnetic field of the instrument. So, the actual shift, what is now the actual shift of acetone? What you do is simply you took the actual shift of acetone is nothing but the difference between whatever you get in trimethylsilane to the one which you get in acetone. So, this is the actual shift. So, this actual shift, sorry, this you may be nomenclating it differently. So, the actual shift is what we are actually getting in the NMR spectrophotometer. So, now let us see one example, which is the phenyl acetate. So, why am I taking this example? Because it has a phenyl group and acetate groups, and both are expected to lie around different chemical shifts. Okay. So, as I told you in the earlier class, this will have a ringing effect. The ringing effect goes with time, sweeping with time, and it decreases. So, there is a relaxation of the nuclei. So, now if you see the structure of this phenyl acetate as given below, so you see the different protons having shifts at different location. So, this is 7.23, 7.3, 7.26 like that, while those which are not connected to the aromatic ring, they are having a lower chemical shift 3.45 and 1.89. So, 1.89 is the methyl group and 3.45 is the methylene group. 1.89 somewhat gets here and 3.45 here, and remaining all these are clubbed together. We say these are all equivalent protons, because not much they behave the similar manner. They get visible in the longer chemical shift, or we say that it is deshielded to a larger extent as compared to the other hydrogen. So, it means that whatever we are getting in this particular spectra, it has many hydrogens. So, these particular peak, the decay which is showing here, it has different hydrogens coded within it. It is a superimposition of the numerous frequencies, which is what we use a Fourier transform. It is similar to like the FTIR spectroscopy. You apply a Fourier transform which will extract and convert the signals constituent components to frequencies. So, it will decompose this FID, this decay, into its constituent sine or cosine function. As I told you just now, the some protons are equivalent. Let us say we take the case of benzene and cyclohexane. So, if you see benzene, these all the atoms are within the aromatic ring. So, what happens is that if it is within the aromatic rings, you cannot distinguish each proton from the other. Okay. So, you cannot distinguish these protons from the other. So, it means they are equivalent, means they will show up at a particular place within the spectra. So, now issue is, the question may come that why is it showing at the extreme or the showing at a higher chemical shift, why not at close to 1 or 2. This I will be taking up in the next class, where I will explain you what is the diamagnetic current and what is the diamagnetic anisotropy. So, because of the orientation of magnetic field, you have this particular effect. So, I will not take up now, I will explain it in the next class. Issue is, we have to look up that these are all equivalent protons. So, it will show up in a single place. Now, this and this, the one without the pi electrons, the cyclohexane, because of absence of pi electrons, it is showing a chemical shift very less. It means it is shielded to a larger extent. So, that is what you mean. So, it depends upon what is the aromatic ring. If it is aromatic ring and if it is unsaturated one, so you will have difference in the chemical shift. Likewise, let us see what are the others we can see, examples of chemical or magnetic equivalence, like methyl ethanoate or paraxylene. See, this is methyl ethanoate. Okay. So, like you have one of the methyl group attached here and another one which is attached here. So, now you see the shift for the one which is at 3.68, this is due to the hydrogen atoms which is close to the oxygen atom, which is electronegative in nature, while the one which is in close connectivity with the carbon atom is having a lower chemical shift. Why is this? Because see, here you have a oxygen atom connected to that particular nuclei, proton nuclei. So, what it will do is, it will try to deshield it. So, oxygen will try to distort the electron cloud, it will try to pull it towards itself, while in the case of the methyl group which is not connected with the oxygen, but connected to the carbon atom directly, it will not be able to distort the electron cloud to a larger extent. So, because of the valence electrons which are circulating around the nuclei, it is able to shield the applied magnetic field. So, it show a lesser chemical shift. I would like to recall lesser chemical shift means these are lesser frequencies, Higher the chemical shift, higher is the resonance frequencies. Now, let us see for paraxylene. Now, this paraxylene, both these are equivalent CH3 and CH3, while the remaining all are clubbing together at a area which is equivalent to the hydrogen atom of a aromatic ring. So, again the same thing, because we can be inferred in the paraxylene, because of the pi electrons it is getting deshielded. The deshielding is mainly due to the anisotropy, the anisotropy of the magnetic field, how the magnetic field is oriented. We will take up this later, because the aromatic NMR spectra behaves differently as compared to the linear or branched alkanes. So, we will see that later, but only issue is these two are equivalent in nature. It will show up here and the remaining all shows up at the higher chemical shift. Methoxyacetone. So, now you see there are 3 absorption peaks and 3 sets of equivalent protons. Okay. So, now you see there is one equivalent proton here, another equivalent here, another equivalent here. So, all these 3, I mean you can here you can assume that within a solution you assume there are 3 different types of molecules, something like that. Within the same molecule there are 3 different sets of protons. So, 3 different sets of protons are at 2.13, 4.53, 3.30. Because 2.13 is not connected to any electronegative atom, it is showing a lesser chemical shift here. While in this case 4.53, it is connected to the oxygen atom in the neighborhood as well as to the carbon atom, which is actually sharing the double bond with the oxygen atom. Because of the combined effect of these two, it shows a chemical shift to be in a higher frequency. So, chemical shift in the higher frequency 4.53. While in the case of 3.30, it is somewhere lying in between the one which is methyl group and the methyl group which is attached to the carbon, so to the oxygen atom. So, it is in between 3.30, primarily because it is in contact with the oxygen atom which is electronegative in nature. So, now you see the one important aspect of this NMR spectroscopy is you have a software. With that software you can integrate these peaks. So, if you integrate these peaks, so by definition what it says is that the integral area of the peaks of different sets of nuclei will be in proportion to each other in the way they are present in the molecule. So, what does it mean? Again let us revisit the problem of phenylacetone. Now, you see how many sets are there, A1, A2, A3. What are these A1, A2 and A3? See, one is due to A1, if I say it is due to this set. So, this set is A1. Okay. So, we have 1, 2, 3, 4, 5 protons appearing at this higher end of the chemical shift. Then A2 this is here, this is due to the CH2 group 3.45, this comes up here. This is another set of nuclei, and the third set is represented by 1.89, which is due to A3. So, now you see that there are different sets of nuclei. So, it means if I integrate this area, this is suppose A1, and I integrate this area, this is suppose A2 and this is A3, the area ratio between A1 to A2 to A3, this is what should be 5:2:3. It should be exactly in the same manner through which it is appearing in the molecule. Okay. So, this is what you need to understand. So, area under each peak is proportional to the number of hydrogen generating the peak. So, the ratio is 5:2:3. If you do then calculate the actual ratio. So, this absolute area does not make any sense. What you do is you fix one of the area and then you relate the area with respect to that reference area. So, if suppose A2, if you assign it as 1, so what will be the value of area? That will be A3, and what will be the value of area with respect to A2, that is A1. Now, if you take the ratio of all these 3, you should be having 5:2:3. This is the same as the number of 3 types. The NMR spectrum, so that is what it says. You have a software here which actually integrate the area under each peak. Now, this is where I want to emphasize in the case of chemical engineering. So, in those cases where you know you have some composition and all are organic compounds and you need to know how much of each is present. So, then NMR gives a, I mean I should not say the exact composition, but it is roughly equal to the composition of the different components in a mixture. But yes, if you want to arrive at a particular concentration which are let us say in the range of ppm, then probably I will suggest not to use NMR, but you go with UV. So, that is very important, that is what it says. So, now if you get that type of spectra and you know what are the compounds present in it, how can we measure the concentration of different compounds? See, what happens is the integration of NMR, just now I have explained, tells us the number of protons represented by a given signal. So, the figure of this earlier figure, I mean the figure of the HNMR spectra, I will just show you in the next slide. There are having 2 components, which is this one, the methyl triphenyl phosphonium bromide. This is nothing but you have 3 phenyl groups attached to the phosphonium atom with a bromine anion. This is one of the compound, this is a solid component, and this is ethylene glycol. The ethylene glycol is a compound you must be very familiar with. It is a high temperature thermal media, and also glycol, which is having when they mix together in the mole ratio of 1:4, they become a solvent. Now, we need to know whether when we mix these 2 compounds, do we get any extra spectra? Has there a reaction occurring between these 2 components, or they are simply within a particular single phase with a mole fraction of molar ratio of 1:4. So, what we do is we take a certain amount of sample, we mix it with CdCl3, that is deuteriated chloroform. As I told you, you require a deuteriated chloroform to observe the NMR spectra. So, that is used as a reference peak. So, what is this equation? You should carefully understand. So, it means what? So, Hi and Hi, it is similar to what I just now gave you. For example, if you want to know what is the concentration of A type proton in a mixture of A plus B plus C type proton. So, it will be nothing but area of A type proton by summation of all area, where I goes to A, B and C. So, this area of A type proton by summation of area of all the protons. So, it is a ratio, so it is fixed, it is a fraction. So, from here you will see the mole fraction. Now, for mole fraction you will get the ratio. Okay. Now, this is what the structure look like, this is that salt. Okay. Now, you count how many molecules are there. So, if you see there are close to, in this particular compound, this MTBP, how many equivalent protons are there? The equivalent protons in the case of MTBP is close to 15. I will tell you what this calculation means. 15. 15 means you take up this, and take up this. So, total is 1, 2, 3, 4, 5, then 5, then 5. So, 15. So, total 15 hydrogen atoms of this salt gives an area, because the issue is this particular peak is due to CdCl3, that is known, that is by definition it comes here, because there are some amount of impurities of proton. That is why even though there is no hydrogen nuclei, there will be some part of proton which actually makes it appear a very small low intensity peak. Now, both these peaks, the issue is you have seen this is 7.88, 7.88. So, it is supposed to appear here, but we do not know where is 7.88 and where is 7.75. To observe these very separately, then you will be requiring what is the high frequency. So, this is carried out at 400 megahertz. So, what we do in order to avoid that confusion, we assume the total area of this, if I write here A1, A1 is equal to sum of 7.52 plus 30.36. This is what I have done, 7.52 plus 30.16. This you divide it by, so what is the contribution of one proton? So, if the total area is this much, divided by number of protons, 15. So, it means this is the actual area as assigned to one proton of the particular salt. Now, issue is, now is this correct? Because I have got a value 2.52, but I will say that okay, this is fine, but you know, there are other peaks also. Let us say you have the peak here 3.18, this is also something which is to be seen, because this is CH3. Now, where is this peak located? This peak is located right here. So, if you see the peak here, CH3 is located right here, this one, because this is as compared to the phenyl nuclei, the atoms or the hydrogen nuclei in the phenyl group, it is having a lesser chemical shift because of the aromatic ring current. Because of this, it will show up in a region of 3.82. Now, see this number, does it actually match? Because both these nuclei lie in the same molecule. So, it means the contribution of nuclei as per area should be the same. Let us cross check that. So, you add this 3.82 and 3.81. And then you divide by how much? There are 3 atoms here. So, you divide by 3. So, that is what you get. You see, you get 2.5. This is 2 point. Almost they are matching with each other. So, we can clearly say that this one and the one which is this one corresponds to that particular MTBP, that is methyl triphenyl phosphonium bromide salt. Now, let us see what are the others. So, that means that these 2 peaks are assigned. Now, what do we have left? The left one is the one due to these molecules, ethylene glycol molecules. Now, the issue is this is 3.41, because these are CH2, these are CH2 groups which are connected to the oxygen atom. So, those hydrogens which are connected to the oxygen atoms, they are electronegative in nature, and this CH2 and CH2 they we say as chemically equivalent. So, it means it will show up at 3.41. So, 3.41 means this one. So, this if we integrate this area, it is 38.21. Okay. Now, if it is 38.21, you divide it by how many atoms? 4. Because there are 4 atoms. So, if you divide, you see it is 9.55. Now, the question is this 9.55, what are we getting? So, if you see the areas, we have mixed 4 moles, it comes to 1 mole. So, it means the area ratio between 2.52 to 9.55, 2.52 to 9.55. So, they also will be in the same ratio. So, if you take a ratio like this, it will almost, I mean I will not say exactly, but it will say almost, it is equivalent to 1:4, almost, almost. So, we can say that this and this are in the ratio of 1:4. Now, you might ask me, why haven't I taken OH here? Why haven't I taken OH? Because the issue is, why we do not take OH is, these are very labile hydrogen atoms. So, these do not have any fixed position in the chemical shifts, because it depends upon, let us say, what is the concentration of that particular molecule in the solution, or what are the neighboring atoms in the solution, whether the solution is dilute, whether the solution is concentrated, whether it is in some organic compound or it is in some any other compound like alkanes. So, all this actually makes it very uncertain. So, this peak, even though it is due to OH, it is very uncertain. This may be lying here, sometime it is lying here if you change the composition. So, we do not take this for quantification. So, you take those peak for quantification which can be clearly identified. For example, the equivalent nuclei of phenyl rings and the equivalent nuclei of the methyl groups in ethylene glycol. Okay. So, if I want to summarize, So, those spectra which are now kindly note I have just reversed this, it's actually it should start from 0 to 10, but let us to go for a convention, mathematical convention, is showing from 0 to 10 here. So, those which are closer to, if I 0 I can assign it to trimethylsilane, those which are closer to 0 which are having chemical shift 0 with respect to TMS. So, these are of lower frequency, as I told you it will absorb in a very low energy, while those which are to this end it is higher frequency. Okay. So, it should be this one, it should be deshielded, because if I, so those which are appearing here it should be deshielded, and this one towards the trimethylsilane it will be shielded, because shielded means what? Just understand, the shielded means it is able to withstand the applied magnetic field. If it is withstanding the applied magnetic field, it means the electron cloud is not distorting, or in the case of deshielding it means the electron cloud is distorting. So, the particular nuclei electron cloud is attracted some other direction. So, which means that it is deshielded. So, it will try to align with the magnetic field and it will show a higher resonance frequency. So, now let us see some more examples of the chemical shifts, and this is what it is ppm. So, this is 2-methyl propanol. So, in this case you have different groups of atoms and different groups of nuclei, 3.49 because of the presence of oxygen atom. You have a CH3 group because you do not have presence of any other atom. So, it will show a very lower chemical shift. So, these both A are equivalent. So, it will show up in the highly shielded region. In the B it is probably little shielded, it will show somewhere here. Now, how these peaks are splitting, that I will tell you later. Okay. So, this is what it is, and OH group, because it is, as I told you, it is labile, we should not take this as a quantification, but somehow we can allocate this in this particular spectra if you take it in a comp. So, this is C peak, and D is quite evident because of the electronegative atom, it shows up here in propanol. Likewise, same thing I will not repeat here, the pentane, most of the peaks of pentane are somewhat shielded because you do not have any electronegative atom. So, we can say almost the ones which are terminal methyl group, they are equivalent. So, they show up and they are shielded to a high extent, while those which are not at the terminal end, which are in between the chain, it is less shielded. So, they show up here. So, these are all the spectra which are. Now, if you have the alkene, the phase, the double bond, this will somehow be deshielded because of, as I told you, with the existence of a pi electron. So, the deshielding increases because it may work up in a different manner because of the anisotropy of the field. So, that is why you have some peak which is connected to this alkene group to be here somewhere. So, these are equivalent in nature, is showing up at 5. Remaining is a similar way you can define it for the, this have higher shielding. So, it shows up in a lower region. Chemical shift for benzene, I will show you, I will discuss this in details in the next class, where why this occurs, because all the benzene rings have a ring current. Because of this ring current, it attracts or it interacts with the applied magnetic field, and because of this applied magnetic field, there is some effect happening. So, there is the magnetic field is not uniform. Because of the unsphericity or the ununiformity of the magnetic field, these actually chemical shifts occur. Now, if you have a chlorine atom attached to the benzene ring, like here chlorine atom here, and so sometime you get the peaks to be shifted. So, in this case benzene, when nothing is there, you have at 7.2, while if you have some attachment or substituted something which is showing up here. So, this methyl group will show up at the lower shielding area, that is E. Okay. So, different depends upon the constituents, substituents of the particular spectra. So, if I want to sum up, where do the spectras like? See, the carboxylic acid is the most deshielded part. So, COOH organic acids will somehow show in this spectrum. Then you have the CHO aldehydes, which will be showing up between 9 to 10 roughly, because see many things do also here occur, that is how strong the solution is, whether it is dilute, whether it is concentrated, but somehow the range is between 9 to 10, unlike in IR spectroscopy where you have a fixed value of this thing range, it is not something, it may differ between 9 and 10. Then aromatics and chloroform somewhat between 7.2, alkenes depend upon the length of the carbon chain lying between 4 to 5.5, something like that. Then alkyl halides because the electronegative atom somewhere here, then conjugated alkanes such as the isoalkanes somewhere here. Then OH, NH, as I told you, they are very labile, so they can be either moving here and here depending upon various factors, whether they are concentrated, etc. And then the linear and branched alkanes, these are the most deshielded ones, and they will be lying up somewhere in this region, just close to the 0 chemical shift. So, I come to the end of this particular lecture. So, in the next lecture, we will see the examples of spin-spin coupling. How does this spin-spin coupling actually affect the magnetic field and how we determine the spin state. Thank you.